I'm Jeff Lendermon, application engineer and plastics specialist for GoEngineer. I concentrate on the injection molding simulation software. Welcome to my webinar, Good Parts Hinge on SOLIDWORKS Plastics. So I've been in the injection molding industry all of my career. From the time I was in college, worked all the way up through 30 plus years of injection molding, anywhere from the quality control department to production planning and into tooling design, and all the way up to the president of an injection molding company. I came into GoEngineer 5 years ago to support the injection molding simulation software and the mold tools within SOLIDWORKS. I had a lot of experience with SOLIDWORKS, started using it in around 2012. In my career for a long time, I've seen a lot of the living hinge designs, anywhere from dental floss containers, flip top caps, water bottles, gum containers, all of those things. Several parts I've seen, there's some parts that have 3 different living hinges on them. It's really a good product to actually reduce the amount of assembly that you have and also reduce mold costs. You're not having to mold multiple parts. You can do a single part, one mold. Everything folds together, snaps together, and things like that. So our living hinge has been around since the early 60s. It's been implemented into many part designs, as I said, dental floss cases, flip top lids, water bottles, gum containers. We've seen now medical hemostats that are used, just for a few of the examples. But there's some key factors to successful molding of living hinges. I mean, even with the design being that old, that design that was created in the 60s, 40 years ago, is very robust, and everybody's always been following that design because there's no reason to redesign something that works, right? So what I'm going to show today is the typical geometry of the living hinge and what it follows, that 40-year-old design, and injection molding guidelines that will help produce quality living hinges. In materials, really, there's just a few materials that living hinges work with. The most popular is polypropylene. There's some applications that utilize nylon and some applications that use polyethylene. It's a flexible material. It's not rubbery flexible, but with the living hinge design, you're able to flex it many times without it breaking. And then we'll also look at the injection molding simulation utilizing SOLIDWORKS Plastics, the simulation software. So the first thing is our living hinge geometry. So our geometry proportion to the living hinge that we show here has been around for 4 decades, as I said. The hinge's thickness, radius, and length all need to follow this basic setup. So our keys are the thickness, the 7 to 15 thousandths thickness, the 30 thousandths full radius, and this flat on the top of the hinge. So within the 7 to 15 thousandths inch range, thickness range, a restriction to the melt flow occurs that causes the plastic molecules to orient to where they're perpendicular to the flex direction. What this does is allow those molecules to actually bend and stretch without messing up the molecules. The full radius at the bottom, that 30 thousandths full radius, is important. It allows the material to flow through there properly, and it also allows the part to hinge all the way over and bend at the apex of that 30 thousandths radius. So it'll fold over to a flat. If we look at the top view over here on the right, the top view, if we radius those edges, it'll actually improve our hinge tear strength as well. So that's part of the design that goes into it. This hinged flat section at the top, the 0 to 6 thousandths. So this allows us to actually adjust some things. So a lot of times this will be machined flat, and then we can go back in and remachine it or take material out of it to change some of that thing. So a lot of times if you start too thin, it goes back and you have to remachine it to make it thicker and thicker and thicker, utilizing the simulation, we can reduce some of these steps though. So some of the injection molding guidelines. So everybody knows that the uniform wall thickness guideline to good molding practices, you always want to have a uniform wall thickness. Well, the living hinge violates this. You're running through an extremely thin wall. So there's some guidelines that we follow for successful living hinges in the molding. There needs to be a uniform flow direction through the hinge that will cause the polymer, this causes the polymers to actually align perpendicular to the bend. So our flow needs to come through the hinge where it feeds through the hinge all at one time, all at the same velocity, all the way across the hinge. That'll give you the most robust design, and you'll be able to cycle the bending and flexing way more robust. So it'll be a much stronger design. So this restriction helps us orient the molecules. It also creates a pressure drop on the far side of the hinge. So this is going to lead to lower cavity packing pressure on one side of the hinge versus the other. So some of the things that we need to remember during this phase is if I have bosses and ribs and things like that on one side of the part, I don't want to put them on the opposite side of the hinge because it'll be harder to pack them out. We'll have sink marks behind them and things like that. We also have to look at the shrinkage difference between those two halves, especially if they're fitting together, right? So we want to be able to analyze those things and work with positioning that. So one thing that we can also do is change our gate positioning or actually add multiple gates to help with the pressure drop. But if we add multiple gates, we need to keep in mind though that with multiple gates, we're creating two flow fronts. You have two material flow fronts that come together, you're going to have a weld line between them. So this weld line is actually going to cause some issues with in the part. If our weld lines come together in the hinge, that's an area where you're trying to flex multiple times, right? So you don't want the weld line to actually happen in the middle of the hinge. If you proportionately put your injection locations where your weld line hits there, you're going to have a weak part. It's most likely your hinge is going to fail. In our restricted area also will cause shear stress in the material. So your material's flowing through there and you have shear stress on the plastic material. That could cause degradation in the material if your shear stress is over the maximum recommended shear rate and shear stress for that material. One thing though that shear helps with in material through a molded hinge is you get shear heating in the plastic. So you have the plastic flowing through the part, it hits this restriction, it starts heating up. It heats up and flows more smoothly through the hinge, and then it'll start cooling down again. So, but you just want to make sure that your shear stress and shear rate don't go over the maximum, or you're actually going to overheat the material and then it'll start degrading, and then you're going to have a weak hinge. So there's a balancing point in there. So we have to look at all of those things with our thicknesses and everything. And finally, another injection molding guideline is our mold cooling. So we always know that mold cooling is important in the molding process. Proper cooling channel placement allows for uniform cooling throughout the mold. It produces consistent quality. It's critical to place cooling circuits as close to the hinge area to provide consistent temperatures in the hinge during solidification. That way you get the most consistent result every time. You're going to have a more robust design, you're going to have better quality parts, and your hinges are going to last a whole lot longer. And now we'll look at SOLIDWORKS Plastics. This is our injection molding simulation that's built into SOLIDWORKS. It's an add-in for SOLIDWORKS. Using SOLIDWORKS Plastics mold filling simulation to determine our ability to fill, our weld line locations, our shear stress, and our pressure losses are going to validate our part and tooling designs. So the earlier we do this in the process, it's going to reduce our costly rework and testing that we have to do on our living hinges. So our keys to getting accurate flow prediction through the living hinge feature is to be sure to refine the mesh in the area. So refining our mesh in SOLIDWORKS Plastics is really easy. I really like the mesher in SOLIDWORKS Plastics. We have a really good mesh control. We have very good advanced mesh control as well. So all we would do is select the faces we want to apply a finer mesh to, set our mesh size, and create the mesh. So there's a couple of different type of meshes that we have the availability in for injection molding simulation. There's a shell mesh and a solid mesh. The shell mesh would be good for meshing just the surfaces of the model, and then all the calculating is interpolated between these surfaces for the calculations of flow. The solid mesh creates a full mesh throughout the thickness of the model. So using a solid mesh will give us a more accurate control and consistent results when working with parts with non-uniform wall thicknesses, such as living hinges. So if we look at the cross-section of our mesh through the living hinge, notice that I've got a lot finer mesh through the living hinge. It gives us a lot more elements through this area. So this will actually show when I'm looking at my flow orientations and I'm looking at the flow pressures and the temperatures through my model, it's calculating that through all of these little tiny nodes in there. So I get more accurate results and a lot more robust results in those areas as well. So earlier I pointed out some injection molding guidelines to follow, right? SOLIDWORKS Plastics can analyze the part model for these guidelines for designing and building the mold. So one of these was to prevent weld lines from forming in the hinge area when multiple gates are used. So in this example, if we watch or oriented, our weld line shows up right in the middle. So by changing the placement of the injection locations in the simulation, I'm able to actually move the flow of the material so it flows across the hinge from one side prior to hitting the other side. So my weld line's not in the middle of the hinge anymore. So I get a more robust hinge, and it actually makes my weld line an area that's less visible on my part. So I'm going to have a better part design, a less visible weld line, and a more robust hinge in this case. Some of the other results we have, we were looking at the fill time plot to watch the flow, the pressure in the fill. I talked about the pressure drop between the two cavities. So it's going to identify the pressure drop by looking at my pressure in the fill. We also want to make sure that with our pressure, we're not actually limiting out the injection molding machine. So in this case, my pressure is 70 megapascals. If my molding machine only had a 100 megapascal limit, I would be closer to the top of that limit. We want to make sure that we're not at that higher range. We're less than 66% of the maximum on my machine. So I may need to adjust some things, enlarge my gate size or slow down my fill rate, or maybe even thicken my hinge a little bit to adjust those limits. But I have the ability to look at those within SOLIDWORKS Plastics. We can also utilize the measure tool in plastics. So the measure tool allows me to actually place points on certain nodes within the hinge, so I can look on either side of the hinge, and it will show me the difference in pressure from those two sides of the hinge. So the velocity vector is another one. You can turn it on. We can look at it with the fill time plot behind it. This is another one we can look at. So my velocity vector at end of fill. It's going to show me the orientation of my flow front going through my hinge. It also will show me flow increases. So as the material flows across there, shooting through that thin section, the shear is actually going to increase the flow just slightly as it goes through there. It's a good thing, but we're able to actually look at the orientation. Remember that that thin hinge is, we want it to orient where all of our orientation of the molecules is going directly across the hinge all at the same time. And we can look at that. We have the ability to adjust the vector number and vector length. If I had them slammed all the way to the right, we would just see all these blue things on there. So I'm able to adjust them so I can look at them actually through the hinge as well as I need to. In shear stress, at the end of packing, I talked about shear stress earlier. It's going to show us the increased shear through the thin area of our hinge. We want to make sure that we're not exceeding the recommended shear, which would lead to material degradation. So I talked about that before. These max shear rates and max shear stresses are, they come from the material database and the manufacturer's recommended amounts. So in this case, this polypropylene material I have chosen, my maximum shear stress, 0.252 megapascal. If I look, my maximum is actually 1.36. So with this thinner web through my hinge on this particular model, just to show that the shear goes through there. So I could go through and make a different configuration with a thicker hinge and actually reduce that shear stress as well. Another good thing, there's XY plots in SOLIDWORKS Plastics. I can look at my melt front flow rate. The melt front flow rate is going to show you the rate of flow through the part. And notice in this case, it actually drops down between this 0.6 and 0.650 seconds. That's actually where I have my fill time set at 0.62. We can see that flow rate drops when it hits my hinge in this case. It's going to drop and then hit the hinge and then actually increase again on the other side of the hinge. So this is going to allow you to look at the flow rate through the part. If you have a flow rate that stalls out, your plastic will start to solidify. You may end up with flow marks and things like that on the part, but it's going to give you an idea of where your flow rate changes. We have the ability to go in and change our, have a multi-stage flow rate. We can go in, adjust our flow rate from the standard when it hits that point, increase the flow rate as it goes across the hinge, and then drop it back down again to keep a more uniform flow rate. But this tool allows us to actually analyze that and then see at what point that happens. Another good way to actually analyze the part, make sure that you can make these adjustments at the machine. Another good, easy thing to look at, quick and easy, the gate filling contribution. When I'm looking at multiple gates on a part, this is an example of the first one I had where I had the weld line right in the center. So my gate filling contribution shows that the gate that's filling this side and the other side are meeting right in the middle of my hinge. My new gate location, when I moved the gate location on this side closer, it actually filled all the way across the hinge. So I can see that my gate location is they meet down here at this point now. And then finally, the cooling analysis in SOLIDWORKS Plastics. So this allows us to determine temperatures, part cooling times, and coolant flow velocities. So these can all be used to determine our best placement of cooling circuits to provide the most uniform temperature and part cooling. The cooling analysis is part of SOLIDWORKS Plastics Premium, so it's the highest level. The cooling and warping analysis are part of those. Everything else that I've done up to this point, the filling analysis is part of standard. The filling and packing analysis are professional, and then the premium version contains fill, pack, cool, and warp as well at the same time. So I'm just going to show a little of the user interface now. SOLIDWORKS Plastics is an add-in, so it's built into SOLIDWORKS. It's an add-in just like any of the other simulation tools, SOLIDWORKS routing, flow simulation, inspection, MBD, all of those things are add-ins. Plastics is another add-in. The nice thing about having plastics as an add-in, once I go through and set up my analysis, I have the ability to come in and duplicate a study. A duplicate study will actually create another configuration of my part file. So I've got all of these configurations which are actually plastic studies. It allows me to change geometry, change materials, change any settings, add the cooling channels, or so I can work through just by adding these duplicate studies. So once we actually get a study set up, the user interface is really intuitive and easy to use. The first thing I would do is start a new study, specify what material is going through my injection unit. My injection unit also allows me to set my fill and pack settings. The next thing I go through and specify what part is my cavity. Then I also can design my cooling channel lines based off of sketches. So if I just have sketch lines in my model, I can actually tell it what diameter those sketch lines are, and that's going to create my cooling channels. I also assign what material, water, going through my cooling channels. When we're doing cooling, we also have a virtual mold. So this keeps me from having to have the full model of the mold. I can specify what material it is. It's going to account for the thermal properties of the mold, of the water going through the mold, and the thermal properties of the hot plastic in the mold when it's doing the cooling analysis and the warp analysis. Next step would be to set our boundary conditions. So I can set my injection location, I can come in, I will set my coolant inputs, so my ins and outs, my coolant inputs, my temperatures and flow velocities. Since the cooling analysis is a full 3D CFD analysis, I can set my velocities as well. There's some global parameters that we can set, like room temperature, so the orientation of the part in the mold, the orientation of the part as it cools on the table, and some basic cooling things that we set as well. And then we would come in and mesh our model. Remember, when we mesh our model, we want to make sure that we're actually refining the mesh around our vent area, our hinge area, not vent area. And notice that it's automatically refining around some of the curvature-based things I have. That's actually a setting that we have for curvature-based mesh. Once we get that, then finally we can come in and choose what we want to run. With SOLIDWORKS Plastics Premium, I have the option to run the cooling analysis, flow, pack, and warp. We can run them kind of in any order. So typically I'll run flow first to be sure my part's going to fill, and then I start going into a more advanced analysis. And then finally we get to our results. So we have flow results, pack, cool, warp. Our XY plots, I showed you some of those. And then we have a summary and report, which will actually create our reports. It'll create an Excel or a PowerPoint presentation and a Word document with custom templates as well. And always remember, GoEngineer has offices all over the United States. We have application engineers and technical people and salespeople all over the United States. So we're always here to help you. There's offices located in all of these areas. And GoEngineer provides many different avenues for training and resources. We have classroom training. Depending on your area, we just opened up classroom training here in Texas where I am. Some places are still limited to classroom training, but we have provided online training. We have online resources. Our knowledge base, our YouTube videos are incredible, and we also have certification programs. Our award-winning tech support services, SOLIDWORKS training. We also have print part services and other services that GoEngineer is now doing. We're hosting PDM servers. We have PDM implementation, rendering and animations, and some CAD automation that we do. So always remember, sign up, subscribe to GoEngineer. You can follow us on social media, keep up to date on more webinars, blogs, training, and content. If anybody has any ideas of any other type of content they want to see or any webinars, reach out to us. We're always looking for things to do.